Hello, everybody. Hopefully you can hear me. Anybody out there? Okay. Welcome to the first OCGS virtual luncheon of the year. Appreciate everybody joining us today. It's always nice to kick off the year. Today we have Dr. Lynn Soreghan joining us for this luncheon to educate us on the deep climate of the Permian, deep time climate of the Permian. Before we get started introducing her, though, I'd like to take a couple minutes to speak about Mike Pollock, one of our local geologists who's recently passed and is heavily involved in OCGS, serving as a director at one point, and as well as serving his alma mater, OU, participating on the Alumni Advisory Council for the School of Geosciences. If you knew him, you knew he was passionate about exploration, oil and gas in general, and the importance of small independent companies to the oil and gas industry. So just keep him and his family in your prayers these next few weeks, and we'll be missing him. So with that, again, I'd like to thank our sponsors. Hopefully you've seen the sponsor sheet being advertised or highlighting the sponsors for the OCGS. I appreciate their contributions. They definitely help support the society and make it happen for all of us. And also we were showing upcoming events so that you guys can get a heads up. So next 2 months of talks, as well as a Valentine virtual wine tasting that our social chairs put together. Hopefully you can join us for that. Okay, with that, saying all that, now I'd like to introduce Dr. Lynn Soreghan. And I have a short bio, if you haven't seen it. Dr. Lynn Soreghan is the director and Eberly Family Chair, as well as the David Bourne Professor for the School of Geosciences at the University of Oklahoma. Lynn uses sediments to interpret the Earth's deep time climate with the interest in ancient glaciation, atmospheric dust, and weathering. She earned her BS in geology at UCLA and her PhD in geology from the University of Arizona, and subsequently worked at Amoco before joining the faculty at the University of Oklahoma in 1996. So without further ado, Lynn, would you like to take over? And
yeah.
I would say if you have questions, please type them in the question box, and Chris Wiggers or I will interrupt Lynn nicely and read those out so she can answer as we go. Thank you.
Okay. Let's see, I'm going to get my, trying to share it here. Okay, here we go. See if that's working now. Can you see that okay?
Yeah.
Okay, thank you. Thank you. So thank you, Raleigh, for that nice invitation and nice opening. Thanks for sharing some memories of Mike Pollock. We've had a couple of sad announcements, from alums of our department lately. So keeping them all in our thoughts. But thank you very much for inviting me to the Oklahoma City Geological Society to present on this topic that I'm calling deep dust, and that the reason for that name will become apparent a little bit later. I'm starting with this picture, these two pictures here. One from Oklahoma. Many of you may find that one very familiar. It's the Glass or Gloss Mountains in western Oklahoma, exposing some of the Blaine and Flower Pot. And then down below it is a photo of units in the Lodève Basin of southern France, same age, and remarkably similar. You could look at these two and almost not know which one is Oklahoma and which one is France, except for the differences in maybe the production of organic carbon types there. But we've been doing work in both, of course, Oklahoma for some time now. And for going on, 8 or so years in parts of France on similar age strata. And so that's what I'll be talking about today. So there's this great quote I like from over 100 years ago, Earth History book by Chamberlain and Salisbury. Between a marvelous deployment of glaciation, a strangely dispersed deposition of salt and gypsum, an extraordinary development of red beds, a decided change in terrestrial vegetation, a great depletion of marine life, a remarkable shifting of geographic outlines, and a pronounced stage of crustal folding, the events of the Permian period constitute a climacteric combination. Each of these phenomena brings its own unresolved questions, while their combination presents a plexus of problems of unparalleled difficulty. More than any period since the Proterozoic, the Permian is the period of problems. So I love this quote. I love the alliteration in it, but I love what it's saying, that there's so much to know about the Permian. And of course, it was a 50 million year time period, so a lot went on. But I like to point out in particular that it is literally the last time, the only time in Earth history, in all of the 4.5 billion years of Earth history, that we've captured the collapse of an ice house and transition into a greenhouse on a planet with you could call it near fully developed terrestrial biosphere. That is, we had plants, we had land plants, and we had a lot of animal life, similar to what we have today. It's our only example of that. So I think there's a lot of that reason and a lot of other reasons to study the Permian. I'm going to start with this. Why am I studying this? What is dust? What do I mean by dust? I've got a little image down here of a human hair. Hopefully you can see my cursor. Maybe Raleigh, you can let me know whether you can see it or not. And so human hair showing some fine sand here, and the diameter of a human hair, which is about 50 to 70 microns.
I can't see your cursor, Lynn.
Okay, thanks, Raleigh. Sorry about that. Or you can't. I'm sorry.
I cannot.
Do not. I'm sorry. Okay. Well, in the lower right, then is this image, a graphic image of just the human hair, and what that is, which is 50 to 70 microns. And you guys are geologists, so we're used to thinking about microns and so forth. That PM 2.5 is particulate matter with 2.5 microns and below, which is that's the material that's really, really bad for us. It can cause a lot of respiratory issues and so forth. PM 10 is particulate material, 10 microns and below, a lot of the dusts and pollens and molds and so forth. Basically, what I tend to use as dust is a catch-all of material less than 62.5 microns. Why 62.5? Well, that's the cutoff between sand and silt, sand and mud, if you will, meaning silt and clay below that. And if that is blowing around in the air, we call that dust. And if it gets deposited as dust, we call it loose, German word for loose, this loose material, powdery material. It travels in suspension in the atmosphere. So unlike sand, which saltates and bounces and builds up into dunes and so forth, if there's enough of it, dust doesn't do that. It travels in clouds, and when it comes out and is deposited, it is deposited out of suspension, which basically means that a dust deposit is typically structureless because it's falling out of suspension. So it doesn't saltate, so it doesn't give us ripples or dunes or anything like that. And then we can call it loose if it's trapped ultimately as a terrestrial deposit, or if it falls into a pond or a lake or mud flats, it can kind of fall wherever it's going to fall, right? In Oklahoma, we've got an infamous history of dust, the Dust Bowl, of course, and we still get these storms that come roaring across, especially the Texas Panhandle when we get our springtime thunderstorms and so forth, picking up this dust material and depositing it. Now, what's the significance of it? Well, it forms both an archive, a record, and an agent of climate and climate change. So despite being a continental deposit, it can basically preserve a temporal fidelity that's akin to a lake deposit or a deep sea deposit. So you can have really high resolution from these deposits, even though they're continental, and we tend to think of continental deposits as pretty gappy. I recently saw this image, I think because of COVID and so forth, and I grabbed it just because I thought it was a really cool image of particle sizes and pretty relevant. The coronavirus is on there, so you can see the coronavirus, even though viruses are too small to be colors, so the red is all human imposed. But the material that I'm talking about really is the material that would be here in the range of white blood cells. That's actually the 25 microns, 30 microns. That's the common mode of the loess deposit, as well as pollen grains and so forth. Nice visual. So back to dust, the relevance of it. I say it's an archive of climate and climate change. So the picture you're looking at on the left is of the Chinese Loess Plateau near Xi'an, China, and Luchuan. And the L's and the S's on this image are showing where the loess is versus where the soils are. Of course, it's really all loess, but there are time periods when there was less dust coming in and therefore a soil developed. So even just looking at this image, you're seeing climate shifts. The loess were the dusty times, the soils were the less dusty times. It turns out the loess were northern hemisphere glaciation times, and the soils are interglacials. Okay, so that's accumulated in the Loess Plateau. You can also see dust accumulated on tops of glaciers. This is in the dry valleys of Antarctica on the right. And you can see the dust just sort of as the tops of the glaciers melt during the austral summer, they look really dirty because of all the dust that's accumulated through the year. Of course, this also gets trapped in ice cores, and you can use that to reconstruct atmospheric circulation by knowing the provenance of the dust. So going back to the Loess Plateau for a minute, back in about the mid-'80s, about 1985, a really quite amazing discovery was made, and it was about the magnetism of the dust. And what happened was George Kukla, person who was working a lot on the Chinese Loess Plateau, went in and looked at the magnetic susceptibility of the loess deposits. And it turns out that you can date them well, because you can date them using magnetostratigraphy, and then you can put that together with the susceptibility. And when he looked at that, he realized that it perfectly correlated to the Pacific Ocean record of glacial and interglacial times. So that was the first time that basically we realized that the Loess Plateau was such a high fidelity record of northern hemisphere glaciation. And it went loess, soil, glacial, interglacial, glacial, interglacial. That was the beginning of really using loess records as a high fidelity record of climate change. Again, what's nice is that it accumulates like in a deep sea core or in a lake deposit, unlike a fluvial system that's cutting and eroding all the time and so forth. You get this really high fidelity record. So it was the first time that we could connect northern hemisphere glaciation and continental climate to the ocean record of glacial interglacial change. Now that was the part of dust that's an archive. So now let's talk about dust as an agent of climate and climate change, right? So this one shows a cartoon image from Winkler and Mahawald. Those are two geoscientists, I should say, who work a lot on dust in kind of the recent record. And what they're showing in this cartoon image is all the different ways that dust can affect the climate system, either directly by, for example, scattering or absorbing radiation, or indirectly by fertilizing ecosystems that affects carbon in the Earth system. So all of the red words on this diagram are ways, either directly or indirectly, that dust can affect Earth's climate system. Okay, so where do we get dust deposits on Earth today? So this shows a global compilation of loess deposits. And you can see that for the most part, you've got a big northern hemisphere record. But what's really interesting about this record is both the ages that you see here, which are mostly since about 3 million years ago, but also pay attention to the latitudes where you're seeing these deposits. You'll notice that they're predominantly high latitude, mid to high latitude. The Luz Plateau of China is actually one of the lower latitude incidences, around 25 degrees. Otherwise, they're concentrated really between about, say, 35 and 60 degrees or so. And then when you go to the southern hemisphere, the biggest deposit would be the Pampean Luz in Argentina, again at relatively high latitudes, 40 or so degrees latitude. If you look at dust, now we're just looking, now I'm using dust more specifically. So the last diagram was Luz, which is just windblown silt, okay, with modes typically around 30 microns or so. Now we're looking at the fine fraction of that, the less than 10 micron fraction, just fine dust. And you can see here now, those descend to lower latitudes. Now we're seeing stuff in the subtropics and so forth. You generally don't get much dust at all in the true tropical latitudes, lower than about 15 or so degrees, commonly 20 degrees. Some of the lowest would be the stuff that you get blowing off of Lake Chad in West Africa here. Okay, now if we toggle between basically where the deserts of the world are and these dust deposits, you can see that these desert regions tend to be regions that match where you get dust lofted off on the planet today. And today, the dustiest place on the planet is considered to be the Baudelaire Depression of what would have formerly been Lake Megachad in sort of central West Africa, right at the edge of the Sahel. Okay, so that's kind of dust and Luz in the modern Earth system. And now let's delve into the late Paleozoic and first remind ourselves kind of what the world looked like back then. So I'm using these maps from Chris Scotese. And we'll start with sort of the tectonic picture. So if you look at the tectonics, you know, we know that Pangea was assembling. Pangea was coming together, large northern continent, large southern continent, colliding along a central Pangean mountain range that pretty much straddled the equator. So you can see those arrows showing what we're calling kind of colloquially the central Pangean mountains. That would be the Variscan Hercynian systems of Europe, merging into the Appalachian system of the US, and then coming westward into the Ouachita Marathon and ancestral Rocky Mountain systems. So centered, pardon me, my allergies are getting to me. This is centered around 300 million years ago, Pennsylvanian time. Now let's go to Permian time. And by the middle Permian, you've really sutured up the continent of Pangea really well. And in fact, it's beginning to rift apart in some places. And that's shown by those kind of those orange streaks around. Now, if we zoom in a little bit to Western Central Pangea, the part of the world that we're used to, right in the middle of the image there, you'll see the label for the Anadarko Basin, and hopefully you can make out the light kind of dotted lines, the outlines of the states. And you can see on here the big brown area, that's the Appalachian Ouachita Marathon, Central Pangean Mountains, that big orogenic system, I'll say, instead of a belt. Paralleling the equator, and then the ancestral Rocky Mountains uplifts in kind of that gray color, and all the basins that are paired together with those. And as we sutured Pangea together, it really proceeded from kind of the northeast to the southwest. So we're here in Oklahoma and some of the later times of that big suturing. Now, if we now turn our attention to climate of the time, so back to the Scotese diagram again for about late Pennsylvanian time. And, you know, really the thing that dominates here is the ice house. So right around the Penn-Perm boundary, we think was the most intense phase of the late Paleozoic ice age, when the ice sheets were so expansive that at times they descended to latitudes of really in the 35 degrees or so. So they were, quite extensive. There may have also been glaciation in low latitudes on uplands, not at sea level, but on uplands. Once we move to the late Permian, all of the ice is gone. The last bits of ice would have hung out in Australia as late as the Wuchia Pinion, but by the end of the Permian, it was all done. And instead, we saw ourselves in a really different world, very much a warming world, where the equatorial region became anomalously arid, apparently, with, we think, very extreme temperatures. And in fact, mega monsoonal circulation. So instead of zonal circulation, which should have easterlies, like I'm showing here, instead we would have had development of a monsoon, and not just any monsoon, but a double-barreled monsoon. That's where you get a low pressure cell hovering over the northern hemisphere during the northern hemisphere summer, and then alternating with a low pressure cell in the southern hemisphere during the southern hemisphere summers. So it would have disrupted circulation quite a bit. So to kind of summarize all of this in terms of the climate, if you look at the time scale over here, we're showing really the Carboniferous and Permian. You can see the big blue blob that is essentially a histogram of glacial deposits, and the peak of that happening in earliest Permian time. You can see the green line, which is very crudely represented, but nevertheless shows carbon dioxide levels, which were at really geological lows, right around the Penn-Perm boundary during max icehouse. No coincidence there. It was a colder world during low CO2, and then rising to quite high levels by the end of the Permian. And then the yellow line showing tropical aridity. So the tropics became progressively arid through time. So what continental records preserve this? Well, you can guess it, dust deposits. So we're looking at trying to categorize, trying to mine this dust record for 50 million years of time to derive what we can from this dust record, because it's an amazing 50 million years. Like the quote at the beginning stated, it's perplexing. There's a predominance of issues going on. There's the collapse, the only collapse of an ice house on the planet with a well-developed terrestrial biosphere, and then a run-up to the most severe extinction in Earth's history at the PT boundary. So a lot going on. Okay, so now let me take you to some archives, some dust archives that I've worked on for some time. I've been working on paleo-loess deposits from the late Paleozoic for quite a while now. And these pictures show a couple of my favorites. The top one is from the lower Cutler beds of the area right up against the San Juan River near Mexican Hat, Utah, if you've ever been kind of near the Four Corners area, beautiful country. And what you see there is just what looks like, red beds, bedded red beds. But if you look at them close up, you realize that it's massive siltstone. And the bedding that you see is a result of fossil soils. So again, just looking at that picture, you're seeing dozens upon dozens upon dozens of climate changes. Dusty, less dusty, dusty, less dusty. About 250 meters worth there. If you look down below, you'll see a close-up of part of the Maroon Formation, which is more than 700 meters of loess. And again, alternating with paleosols, loess, paleosol, loess, paleosol. And it's quite fun because really it's like paint by color, only geology by color, because the loess is sort of orangey colored and then the fossil soils are redder. And you really don't have to do much interpretation to see the soils. I used to say that these were the thickest piles of dust on the planet, especially the Maroon Formation, which really is probably about 1,000 meters thick. in this area. This is near Vail and near Basalt, Colorado. But then I got to Oklahoma and France, and I think that those are even thicker. Now, the hard part about the Permian of Oklahoma, as many of you know, is there's no economic interest in it, so there's very little core. If you look at the map, that shows basically numbers of meters of Permian core, consecutive core, in various counties in Oklahoma, and there's just not a lot. And then if you look at the stratigraphic column on the left there, you can see the reason why, because there are no red or green dots in the Permian, right? It's overburden. So it just doesn't attract a lot of interest. Compounding that problem is we all know that the landscape of Oklahoma is pretty low relief, and the dips are low dips. And when you combine low dips and a low relief landscape, you're lucky to get a few outcrops like the one I'm showing in the lower right here from Lone Mountain near the Glass Mountains. That's the best we can get, is maybe several tens of meters. So not a lot of core in it. Now, what I'd like to argue to you is that the Permian of Oklahoma represents perhaps one of the biggest piles of dust on the planet. We think that it could record a couple thousand meters of largely dust deposits. These are predominantly fine-grained red beds. They've commonly been called shales, but they're not really shales. They're mudstones, oftentimes massive, oftentimes not very fissile, and so forth. Long considered restricted marine or deltaic, but we've done a lot of outcrop-based studies recently and some core-based studies that suggest that there are really widespread loess deposits or loess that fell into marine or lacustrine environments. But it's like I said, it's not easy to do this work because commonly you're dealing with poor exposures and low dips and so forth. The seismic image I'm showing here is part of a 3D survey that this particular line was published in Amanda Rondott's thesis about 10 years ago or so. And it's a really wonderful line. I'm only showing the very upper part of the line, basically the Permian, because it extends from the keel of the Anadarko Basin on the right over the Wichita uplift on the left, and shows the burial of the uplift. And you can see at the base of the Wolfcampian, that would be the Penn-Perm boundary, you can see that the deformation essentially ended right around then. And then you kept accumulating. And not only did you accumulate in the Anadarko Basin, but you accumulated on top of the uplift. So the Wichita uplift was subsiding along with the basin in Permian time, which is also quite a remarkable thing and makes the Wichita Mountains of Oklahoma one of the most unique landscapes in North America. Okay, what I'm going to do now is take a glimpse at the Permian of Oklahoma by giving you just a glimpse. You can see that the horizons that I'll show you are indicated by the red dots on the strat column to the right. So I'm going to start at the sort of lower Permian part of the section and then progress up in a series of photos to follow here to show you what these look like. So starting fairly low, this is from the Wellington Shale. I put shale in quotation marks here because shales by definition really should be fissile, clayey and fissile, and these aren't. These are massive mudstones. In this case with blocky ped structures, those are pedogenic features of soils. Moving up section, this is from core now, the Hennessy Shale. Again, a massive red mudstone with local pedogenic features, so soil features throughout. Now moving to the Flower Pot Shale and the Blaine Formation. Again, red mudstone with fossil soils throughout. Here's some of I had a student, Allison Sweet, who worked on this a few years ago. You can see some of the evidence she shows in her paper here of pedogenesis, such as the reduced root rhizoliths and horizonation in the soils and so forth. Then the Dog Creek Shale, shown here from kind of near Greenfield. And one of my other students, Tyler Foster, worked on this one. You can see some beautiful slicken sides showing that these are vertic soils, that is soils that would shrink and swell with the seasons because it was seasonal moisture. And then finally, the Cloud Chief Formation up here, which is more of the same, not always massive because many of these show evidence for water lane features, say in lakes and so forth. The Permian of Oklahoma is remarkable because it's not been buried very deeply. So we're able to disaggregate it in the lab and run the grains through our laser particle size analyzer to get a grain size analysis. And these are some beautiful examples of those from Allison Sweet's thesis. Some are finer than others, but you can see that medians and modes here in basically that dust size range. So let's talk about, how do you identify loess or paleoloess? So I've put up several features here that are characteristic. Some of them, sometimes we're looking for a lack of features, but certainly we want to see a particular grain size, which tends to be silty, fine to coarse silt, including clay. So the word mud applies here because it's both clay and silt. Like I said, commonly in modes that might range from 15 to 45 microns or so. Laterally continuous, so you don't see beds that are wedging. You don't see channel-like beds or signs of fluvial action or things like that. Internally massive, common paleosols. So let me show you again a few of these as we go through. This is from the Maroon Formation, loess in Colorado, and this is from a road cut, but it's fractured like an obsidian, like a piece of obsidian. And what you're seeing there really is the massive nature of a loess deposit. Because it's deposited out of suspension, you don't really get bedding. So you can get quote unquote beds that are 8 meters thick, and internally they lack any kinds of sedimentary structures or bedding. You can see here again, laterally continuous nature, no channels, no signs of fluvial systems going on. And again, the paleosols. So the kind of color changes that you see in the background here on this exposure are, when you get up close and look at them, fossil soils. So here's some slabs from, this is the Becky Bounds core that was drilled by Amoco actually in western Kansas in the mid-'80s. And it's a beautiful core. We've studied it and slabbed it. And you can see here, red mudstone. That's all you see, okay? Now there's different sedimentary structures here, and some of these sedimentary structures indicate that there was water lane deposition at times. But we hypothesize that this is essentially was delivered to the site initially as dust. And then it fell where it fell, whether that was on land or whether that was in water, in a lake, for example. Okay, so what I'm arguing here is that there's a lot of dust in Oklahoma, a lot of paleo dust. So you might ask, where did it come from? How did we generate all this material? You've got to generate a bunch of silt-sized material. You've got to transport it, probably by rivers, also by wind, picking up the material off of floodplains. And then you've got to trap it in typically semi-arid regions are good regions to trap dust. So to do this, to figure out where did it all come from, we've used detrital zircon geochronology. So zircons, you all know, are these very durable minerals and fake diamonds as well, right? So you can see a bunch of zircons in that microscope image on the left. And they're very durable, so they can be multi-cyclic and so forth. The way that this detrital zircon geochronology works is that you crush up a rock, you separate out the zircons, and you date lots of them. These days, they can do a lot more than they used to be able to do. They can routinely do kind of 300 grains plus per sample. It used to be more like 50 to 80 grains. But what you're trying to see is, okay, what were the source regions, keeping in mind that recycling can happen, what were the source regions for these. And they're typically displayed in these age probability, these relative probability diagrams. So I'm going to take you through these plots on the right here. On the x-axis is age in millions of years. And this is several stacked plots. So it's 1, 2, 3, 4 stacked plots. And for each given plot, basically the area under the curve sums to 1. And the peak indicates, any given peak indicates both the number of grains of that age, and the sharper the peak is, the more constrained, the more precise those dates are. So the height of the peak indicates both the number of grains, and then the width of the peak, if you will, indicates kind of the spread of those ages. So that's what each plot represents. And then what you see in the blue bars here are with the symbols on, or with the letters on top, is indicating the various provinces that these are coming from. So starting on the right here, the ages that are coming in around 16 to 1800 million years ago, or 1.6 to 1.8 billion, are characteristic of the Yavapai Mazatzel crust of the US. The ages that are between about 900 and 1100 or so are characteristic of the Grenville. That's very much makes up a lot of the crustal basement in the southeast and east of the US. Yavapai Mazatzel, more from the kind of central and west. The NP means Neoproterozoic. Those typify those Neoproterozoic as well as the early Paleozoic grains, typify terrains in the Appalachian Mountains. Okay, so, and you can see these are plotted from the early Pennsylvanian ones down at the bottom through to the middle Permian ones up at the top. We have a lot more samples now, but we see the same thing every time. We've dated a lot of these now. We've dated a lot of samples, thousands upon thousands of grains. And what you see is that this material that buries us here in Oklahoma is not from here. It's not from the Wichita Mountains. It's from pretty far away, mostly the central Pangean Mountains, that is mostly the Appalachian Mountains. A little bit from the ancestral Rocky Mountains, but definitely not from here. Okay, so how did it get here? So let's look at this Blakey image of, you can see sort of what would be, Gondwana land on the southeast here, and Laurentia on the northwest, and then the central Pangean Mountains in between. You can see these big white arrows as well as the blue arrows, and then the equator is going across here. We think what was going on is that we were generating the silt and the mud in these big orogenic belts, mostly the central Pangean Mountains, a little bit from the ancestral Rocky Mountains. And step one was to transport them off the mountains in rivers. Those are the blue arrows. Step two would be to blow them off of the floodplains and blow them off of these systems when they dried through both zonal and monsoonal winds, and then ultimately trap them in this big sink of Oklahoma, the southern mid-continent. Okay, now that's kind of the local story, the Oklahoma story. Let me just show you a few photos or a few images from our work in France, just to kind of get the point across of how similar the material of this age in France is. So we're working here in the Low-Dev Basin of southern France. You can see that on the inset of France on the right. The other inset shows the outcrop pattern of the Permian there, this part of the Permian, the lower Permian. And then what we show here is about 1,000 meters of units that are all mudstone, just like what we see here. Okay, so let me show you some photos of this. This is my student, now doctor, Lily Pfeiffer. She just defended last December. She actually worked this system for her master's degree and then actually came back for her PhD, working in the Saligou formation of the Low-Dev Basin. Once again, massive red mudstone, lots of pedogenic features, no channels, no fluvial features. This is what it looks like a little more close up. You can see a lot of fracturing. A lot of that is tectonic fracturing. Some of that is pedogenic fracturing as well. And then finally, a few photomicrographs and so forth. Here on the lower left are slickensides and one of the paleosols. On the right are some micromorphological features of petagenesis or soil formation. And then, of course, the two photos on top are just showing typically how massive and thickly bedded, if bedded at all, these units are. Okay, so what good is LUS? Well, hopefully you remember that it's a high resolution archive of continental paleoclimate. So, how do we derive data out of it? Well, we can look at several things. We can look at magnetic susceptibility, which it turns out, just as it works in the Loess Plateau, works in these ancient Loess deposits as a proxy for soil formation, which is in turn a proxy for climate and oftentimes rainfall. We can look at variations in grain size to look at storminess of the winds that brought this material in. We can look at chemistry to again pull out information on paleoprecipitation. We can look at provenance to figure out which way the winds blew. So there are a lot of metrics we can do to put this together. How do we access this record? Well, we've done as much as we can on the outcrop, arguably. So we're actually proposing to a program called the International Continental Scientific Drilling Program, a research core. I told you about how core of the Permian in Oklahoma is just pretty disappointing. We've punched probably 1 million holes through the Permian in Oklahoma, but always to get to what's underneath. So there's not that much data. Sometimes it's not even logged, much less cored. So we're proposing to the International Continental Drilling Program, a multinational program, to partially fund a research program to core the Permian. If you want to apply to ICDP, you must have an international team. So we've actually put together a France-US program where we hope to drill in both countries, actually.
Hey, Lynn, we've got a question.
Oh, sure. Go ahead.
Sorry to interrupt. Question is, have you looked at any silts found in the Merrimack, Lower Caney, Sycamore, those formations that are in the Stack and Scoop, which appear to be deposited in a marine setting? Any comments on source, deposition of massive marine silts, etc.?
Sorry, what was the last half of the question?
Any comments on source deposition of massive marine silts?
Oh, yeah. Yes. Basically, I think there are a lot of what we call Aeolian marine deposits out there. In other words, the clastics were blown in, and then just like they fall, we recognize them as loess if they fall on the ground and are preserved as a continental deposit. It's a little harder to recognize whether they came in as an Aeolian deposit when the final preservation environment is marine, but in many cases you can nail it and say, yes, this had to come in as a Aeolian deposit. And I think many of those have, in fact. We've had some students work on some of those and publish a bit on those with that interpretation. So I'm at the kind of end of it here, and just to leave you with this idea that basically we're going to try to do this. We're going to try to do this deep dust project to continuously core the continental Permian, to build an unprecedented record of an icehouse to greenhouse transition and the lead up to Earth's largest extinction event. We've had a couple of workshops, one in Oklahoma and one in France. And these typically take a lot of years to develop because ICDP will not fund the entire thing. They will kind of give you their vote of confidence and fund a small fraction of it. And then with that vote of confidence, you then say, okay, it's considered to have been heavily vetted once they give you their stamp of approval. And then you try to go to the National Science Foundation and the National Science Foundations of the various countries and cobble together the rest of the funding to try to get it done. Our target sites would be the Anadarko Basin in Oklahoma and the Paris Basin in France. Those are shown in the red dots on these maps, which show kind of the different configurations for the early and late Permian. And again, the science objectives are to really get at a lot of what was going on, especially with regard to climate during this time of the Permian, the last time that we had the collapse of an ice house on the planet. Some of these are shown here. So looking at the ice house to greenhouse transition, looking at the collapse of the ice house, looking at the transition to the most extreme extinction event we've ever had, looking at continental temperatures. There are quite amazing things that you can do with the evaporites that we have in Oklahoma, for example, which is reconstruct diurnal temperatures, daily temperatures. That's weather, that's beyond climate, okay? And of course, reconstructing which way the wind blew. Here's some of the information about kind of looking at the extreme biosphere, the microbial biosphere. We can look at the microbial biosphere in the modern, but uniquely, we can also look at it in the Permian because the microbial biosphere is commonly trapped in primary fluid inclusions in the evaporites that we can see in the subsurface. And then some of the auxiliary objectives here would be, can we...
Hey, Lynn.
Oh, yes, go ahead.
Sorry, I'm interrupting.
No problem.
We got a question asking what the estimated budget would be for the Permian coring project. Okay,
good question. Yeah, so the cheapest way to do it is to use a mining rig. As a big rig would get us a bigger core, but at a much larger expense. Right now, we've got a budget for a mining rig approach to go 2 kilometers, and that would be to go 2 kilometers in the basinal part, and then to go about 1 kilometer in the upland area, because again, the buried upland of the Wichita Mountains are unique in North America. It would be a budget of around 3.6 million, which is much less expensive than the Paris Basin target, which is more like 9 to 10 million, in part because they have to go a little deeper for theirs, and in part because of it being in France. I guess all the wine, Sorry, I'm just kidding. It is a deeper target there.
We got another one.
Oh yeah, go ahead.
Why is there no record of a coarser grained fraction, fluvial, deltaic, etc., for such extended periods of time?
Yeah, great question. Great question, which is why this has been so puzzling, because we know that we see evidence for water, right? For water lane deposition. So for a long time, these were considered to be delta deposits, deltaic deposits. I mean, that is an interpretation that's out there. I would argue that it's a confusing interpretation because we don't have the fluvial part of the system. Oftentimes we don't have the coarser grains. It's really the grain size is the first clue that something weird is going on. And really the lack of the grain size, as the person posing the question points out, where are the coarser grains? Well, you can't transport coarse grains, unless you've got tornadoes, right? So the really monotonous grain size that we see here is really, the first clue that something strange is going on or went on. And I hope that helps. Feel free to interrupt again.
Oh, here's another one.
Okay.
How would you classify the Garber and Wellington sands in central Oklahoma?
The Garber has some signs for channelization. So there are places where you could argue for fluvial influence on the Garber. And probably, my guess would be sort of an ephemeral kind of way. The Garber also has a lot of signs for Aeolian sand in places where I've looked at it. So I think it's probably one of the, we actually have a student working on it right now. So it's work in progress, but basically a ephemeral fluvial Aeolian system is probably what's going on there. And perhaps what we would call a distributive a distributary rather than contributory kind of system as well.
Okay, moving from Oklahoma, in the Delaware Basin, the Bone Spring sand units have a very narrow grain size distribution. A lot of, coarse silt to maybe very, very fine sand. Has there been much of any research on, I guess, the primary transport mechanism for that into the basin?
Yeah, well, as probably a lot of you know, the deep water sands in the Brushy, Cherry, and Bell Canyon formations have long been interpreted since really since before the 80s, going way back, have long been interpreted as aeolian source, but with a final deposition into a deep marine, if you will, or fairly deep water environment. The Bone Spring is, basically just below the Brushy. I really don't see any reason why it wouldn't be a similar kind of thing going on.
Okay, here's another one.
Okay.
Sorry, thank you. Where does the Red Cave sand come into the picture in Hugoton Embayment?
Yeah, the Red Cave. I actually have studied the Red Cave in Bravo, or what would be considered Red Cave equivalent, I believe, in the Bravo Dome of the subsurface. That's basically, I'd have to look at my correlation chart to remember exactly. I believe it's in the lower Permian part of the section, and it is also, we interpret it in the Bravo Dome system to be loose. And in fact, there's a paper from some authors in Kansas that looked at the Hugoton and also interpreted it as loose. Paleoloose, I should say. Should I go on, Raleigh?
Yeah, you can go on. There's no more questions.
Okay, sorry.
Sorry, I muted myself.
Finish up. No, that's okay. It takes a while to unmute, I know, these awkward silences. So we're hoping if we get a chance to do this, this research core, we'd like to propose a lot of auxiliary science that could be done, monitoring for seismicity, for thermal properties, data collection for exploring aspects of CO2 storage or geothermal energy, potentially astrobiology, exobiology, looking at Mars analog conditions, tectonics, the exhumation rates of uplands, and of course the paleo environment of the uplands, again, because we have it uniquely preserved, almost uniquely preserved in Oklahoma. And that Anadarko Basin target would be basically in the Anadarko Deep, the keel of the basin. And we'd be looking at a variety of ways to put together the dating. The dating is going to be challenging, but I have brand new news right off the presses, if you will, right off the mass specs, that we can achieve really high precision dating in these Oklahoma red beds by looking for volcanic zircons, because we know volcanism was happening, for example, in the Las Delicias Arc in Mexico, and it was blowing at times this way. And so we found some zircons that we should be able to use that as a tool to combine with a lot of other tools like astronomical cyclostratigraphy and magnetostratigraphy after the Kaiman superchron, and biostratigraphy for the lower part of the section and so forth. So that's my little boxes, basically the target area for our drilling. So from here, this project is going towards, a lot of proposal writing, partnerships, trying to find co-funding and in-kind contributions and so forth. But that's a deep dust. And I think I'm pretty much at the end here. I love this picture, which is from Oscar Jacobson, one of the former directors of the Art Museum in Oklahoma, who did these beautiful paintings of Western Oklahoma. So I'll conclude. Consider the possibility, the interpretation that the large volume of fine grain strata, Permian strata in the mid-continent, and in France, the equatorial region of both western and eastern Pangea record mostly continental environments that are basically loess and dust that fell into lakes and so forth. That these have an amazingly an amazing and so far unprecedented high fidelity record of continental climate to give us. We're going to try to drill it, I hope, someday, and we can probably do a lot of auxiliary science with that effort. Okay, so I have a lot of people to thank, people who were co-PIs on our deep dust project. Dr. Ken Johnson, who's been a constant source of advice for me, Mr. Permian of the mid-continent. And I had to put in an Oklahoma shot here during our deep dust workshop, where we brought people from something like, how many was it? Something like 9 different countries from all over. And we were on our field trip looking at, in this case, the Dog Creek, and there was a cow stuck. So we had an international cow rescue happening. And that's what this is, that's what the picture here is of. Okay, I think that's all I've got, Raleigh. So if there are more questions, I'm happy to address them.
Yeah, we've got a couple more questions, and we'll probably end with those two. The first one, actually, we got 3. The first one is do you find any fossil material in the Permian loess sediment?
Yeah, good question. Not much. It's pretty tough, but we do have concrostracians. I always pronounce that wrong. Basically freshwater fossils. We can get polynomorphs under the right conditions. Oftentimes, palynologists say that red is dead, but actually there have been a recovery of polynomorphs from the red beds. There are also things like lungfish burrows, a lot of trace fossils, and actually the occasional vertebrates as well. You would just have to be super lucky to get them in a drill core, of course.
So kind of to add on to that, in terms of the biological aspect of that, but is there any consideration for biological analysis and possible regeneration of bacteria similar to the WHIP site, WHIPP site?
Well, I'm familiar with the WHIP site, but I'm not familiar with, have they recovered, have they looked at microbes in the salt there? Is that what the questioner is asking? We might have to get back with him. Okay.
About that.
We're definitely, but however, yes, in terms of looking at microbes in the salt, absolutely planning on doing that. Yes.
Yes. He answered back, yes, they do.
Oh, cool. Okay. I was not familiar with that, so that's really cool. But yes, we definitely want to do that. The person who's very excited about that and has the expertise is named Kathy Benison. She's at West Virginia University, worked on the Permian of Kansas during her PhD at the University of Kansas.
And then the last question, if the Wichita Mountains are buried by Permian loess with YMDZ from the ARM arm, does this imply that the ARM are younger in age, even though unroofing the Wichitas becomes younger to the SE?
Let's see. If does it imply that the ancestral Rockies are younger? Is that the question?
Yes.
Okay. Meaning the structures on the ancestral Rockies, like the uplift, timing of uplift. If that's the case, I think we have pretty good data from around the Rocky Mountains, including the Wichitas, that the structural deformation was really peaking in the Pennsylvanian, for sure. The uplifts were coming up in the Pennsylvanian. But what we can see from the seismic data is that not that they collapsed because there wasn't a reversal of motion, it's just then everything started coming down. Now in the west, the ancestral Rocky Mountains uplifts do young somewhat to the west and the northwest, so that some of the structural disruption is younger in the northwest than it is in the eastern parts. We do get, because we get some Yavapai Mazatzal grains, that is grains that would be associated with basement that came up during ancestral Rocky Mountains times. We get most of that, where it's most abundant is during the Pennsylvanian. And then the material that we get in the Permian is not as abundant, and it's possibly recycled. So, you know, the beauty, I think, of using detrital zircons for the Paleozoic of North America has been that, for the most part, with the exception of a little bit of sand in the Cambrian and a little bit in the Ordovician, most of the lower Paleozoic section is carbonate, which means that sort of everything was covered with largely carbonate and shales and mudstones, and then, but mostly carbonate. And then the ancestral Rockies started popping up, and we started stripping away all of that Paleozoic cover to get down to basement. And we were stripping away mostly limestones. So when we first began to uncover those basement chord uplifts, we started really releasing lots of zircons, and those would have been first cycle zircons. As you get younger and younger, you increase the possibility that some of those zircons are becoming recycled with time. I hope that made sense.
That sounds great. I can keep up with it, Lynn, so that's
okay.
Everybody else is probably right on top of it. Looks like we got a link to that bacteria.
Oh, cool. Okay.
I'll pass that along.
Yes, I would love that. Thank you.
And then I guess with that, we should probably wrap it up for everybody. I really appreciate you taking the time to share this with us. It's very interesting. And
yeah, my pleasure.
And hopefully we can have you back, you know, to hear what happens with the drilling. You know, if we can get that project executed, that'd be great. So really appreciate the time. Thank you.
Thank you. Thanks for the good questions, everybody. Oh, now I'm seeing them in the.
Oh, you can see them
now. I can see who asked things. Yeah, Andrew. Okay, that was you. I didn't. I should have gone out of the presentation mode sooner, and then I would have seen the questions here. I'm sorry. Great, great questions.
All right. Bye-bye.
Okay. Thank you. Bye-bye.
Thanks, everybody.